So in this talk, I will discuss the detection of unconventional ferroaxial orbital density waves in rare earth tritiorides. So these rare earth tritioride systems, they have been studied for decades, and they are considered to show a conventional charge density wave order. Where the onset of the order can break certain symmetries. So usually the charge density wave break translation symmetry, and sometimes it can also break rotation symmetry as well. But the detection of unconventional order is quite challenging. So because in unconventional system where we have unconventional order, so this order can break additional symmetries, so they are quite challenging to detect. So as mentioned by the Tinkham to introduction of superconductivity, that the symmetry of this gap function can be lower than the lattice. So this is quite important that in quantum material, what symmetries are broken. So it depends on what kind of order we have, like spin order, charge order, orbital topology, or lattice. So how to detect this unconventional order? So whenever this order onsets, so we can have different collective excitations. For example, in the spontaneous symmetry breaking case, we have a Goldstone mode or phase one mode. They appear when these new order onsets, and another is this Higgs or amplitude mode. So this Higgs mode has been detected before in this system, charge density system, but considered as a scalar mode. So it's a boring, so because we have a scalar symmetry of this mode. But recently in our group, we detected our kind of fingerprint of the system, the unconventional system, where this order shows a vector symmetry. So this detection of this vector symmetry tells something that this order is not conventional. There is some unconventional symmetry breaking associated with this order. So by the end of my talk, I will tell you that this axial or vector order, which changes sign under mirror symmetry, has its origin from underlying ferroaxial order, where we have both inversion and time reversal symmetries, but we break additional symmetry like rotational and mirror symmetries in this system. So what are the charge density waves? So charge density wave story started from 1955. So from the Tyrrells, who first talked about charge density waves, that for one-dimensional system, this is a one-dimensional chain of atoms. So as we cool down this one-dimensional system, there is a change in the electronic charge density. So charge density kind of modulates at certain temperature. So this modulation of charge density is followed by the lattice. So they change their position and follow this electronic order. So what we can see in the band structure, that due to this modulation of electronic charge density and the lattice, so this band structure gets folded. As a result of this band folding, so energy is compensated and it opens a gap in the system. So as a result of this order, so we have a new particles, we break the symmetry and that produces new collective excitations. One is called this phase one or Goldstone mode. So this is a gapless mode because it doesn't cost any energy. So this shows the shift in the phase of the order parameter. So another kind of collective excitation we can have is Higgs mode, as I discussed before. To move across the curvature of this Maxwell potential. So these are the fluctuation of the order parameter. So amplitude fluctuation of the order parameter. So it costs a certain amount of energy. So these modes are called gap mode. So if you look over the phonon dispersion of these modes, the amplitude mode, this behaves like optical phonon branch. And at phase one mode, they are kind of positive modes, zero energy at Q0 or long wavelength. But these optical phonons, like optical phonons, these amplitude mode can have a finite energy at long wavelength. And these are optically detectable. We can detect the amplitude mode using, say, Raman spectroscopy or any other terahertz techniques. So the unconventional order has been detected before in different systems, like the chiral charge density phase of this tantalum diselenide. You can see over here we can have left-handed and right-handed chiral domains in this system. So what? Yeah. Which one? Is it moving now? Okay.
Yes. Okay. Yes.
Okay, let me now. Yeah, now you see it, right? Okay, so we can have these chiral domains in titanium diselenide, for example. So what is the chirality is a system, for example, this sphere object. So if we take this mirror image, it looks exactly like its mirror image. So this is not a chiral system. So if you look over your hand and you take the mirror image of it, so if you try to overlap them, they will not overlap perfectly. So that means they have a chirality associated. So similar chiral response is observed in titanium diselenide. And interestingly, we can even tune the chirality, which domain we want. So we need to shine circularly polarized light. So if we shine, say, right-hand circularly polarized light while cooling across the transition temperature, we will have a right-hand chirality. But if we shine left-hand, then we will get a left. So we have a choice to choose which domain we want to have. That's great that we can control and order. So another example is ferro-rotational order in 1T tantalum diselenide. So in this ferro-rotational order, we have similar to chiral order, so we have a two-handedness, but here we don't break inversion symmetry. So even though we break additional mirror symmetries. So this kind of order are detected in Raman spectroscopy. You can see over here that if we change the chirality of light, so the intensity of these modes changes. So this unconventional nature of CDW is further extended recently on this Pogani system, where this onset of charge order break time reversal symmetry because of the loop current in this material, and different magnetic and piezo-magnetic phases can be absorbed in this material. So the question one can ask is, what symmetric condenses can this order parameter reveal an exotic order? So we can detect the order parameter, and if we see the symmetry of the order parameter, if it is trivial or non-trivial, that can tell us that the order which has A2 symmetry. So A2 symmetry is the antisymmetric system has some unconventional order associated. So we can detect, focus on these amplitude modes or Higgs modes of the system. So this is the crystal structure I have studied, this rare earth titerites. So it consists of two building blocks. One is this RTE layer, which is completely insulating, so it's kind of boring. So another is this tellurium layer. So this is the place where this charge order takes place. So it's a quasi two-dimensional system, and one Wall system we can easily exfoliate and reduce the dimensionality of this system. So it has px and py orbital of tellurium. So bands near the Fermi surface mainly come from these px and py orbitals. And if you look over the Fermi surface, we have a quasi two-dimensional system where these bands are not quite straight, but due to the tension. Lattice vector which connects this px to py orbital. The first one connects px to px, and second one connects to px to py, and produce a CDW order in this system, which has been detected long back by a collaborator that using a transmission electron microscope. So in addition to that, this material has very rich phase diagram. If you look over here, so with the substitution of different rare earth elements, we can change this rare earth element of this RTE3. We can actually tune the CDW transition temperature from high temperature to low temperature phase. And also interestingly, with these heavy rare earth elements, this produces a second CDW order, which is orthogonal to the first one. So this is the Fermi surface of this material. We show two CDW transitions. So one is along, say, b-axis. So as soon as the CDW appears, so it takes away some Fermi surface and open the gap. And another is the orthogonal second CDW, which is orthogonal direction to the first one, because some of the Fermi surface is left, and that is taken out by the second Q vectors. So we started with taking for consideration a GDTE3 system, which has only one CDW phase associated with it. So first we detected with TEM that do we detect the CW phase in the system or not. If you look over here, this is a TEM image where we have these bright spots. These are bright peaks, but if you look, there are small peaks over here. These are called satellite peaks, and confirm that we have a CDW order, which is uncommensurate, and Q vector is 2 by 7 times this lattice vector. And so we probe this system with Raman spectroscopy. So in Raman spectroscopy, what we do, we shine a laser light on the sample, and then in the back configuration, we detect this light, and we can also control the polarization of the light. And we can change the polarization from, for example, these two arrows indicates the direction of polarization. They can have parallel polarization, or if we rotate the polarization, we can have a different configuration. It's called cross-polarization configuration. Or we can keep rotating and take from 0 to 360 degree and see how the Raman response changes. So this is the Raman's response of GDTE3 in parallel polarization configuration. So you see there are different phonon modes. Some of them are quite sharp, but this first one at low energy, this is quite broad. So this is a CDW amplitude mode or Higgs mode. And other are the folded phonon modes, because CDW makes a super lattice and that can fold the zone boundary back to the gamma point and produce a new modes in the Raman spectra. So now we thought, let's take a look over the symmetry of these modes. Does they have same symmetry or they have different symmetry? So first we look on these folded phonon modes. We see they are nice fourfold in nature, which has AG and B1G symmetry. So this is the intensity plots when we change the polarization of light in parallel and cross fashion. So they look quite symmetric and scalar. So if we look over the intensity profile of this CDW mode, how it changes, is quite strange. It's not fourfold at all. It's twofold in both cross and parallel polarization. So this blue curve is a twofold response in parallel. So this tells us that we have a unidirectional CDW. CW is in one direction. So that's why we have high intensity in one direction and low intensity in other direction. That is understandable. But detection of this twofold response in cross polarization, this red curve, is quite surprising. Why do we see twofold response in cross polarization? So we try to understand this. If we go back to the Fermi surface, we see there are two nesting vectors. One is QCDW that connects same type of orbitals, say this orange one, px to px, and there is another reciprocal vector which connects px to py. So have a two type of quantum excitation. We can go from ground state to px orbital, and this is connected to another px orbital and come down and gives us px and x called as RAA type of Raman tensor. So another reciprocal lattice vector that connects px to py, so we can have excitation to px orbital, and this will connect it to this by this reciprocal lattice vector and gives us a antisymmetric part. So this is RAB. If we apply a mirror operation on this one, it will change the sign. So then we can have a constructive and destructive interference between these two quantum pathways. So if these two same type of symmetric tensor, they show the interference, they will produce high intensity. So it's called a constructive interference. So they will produce high intensity in our Raman response. But if there is another pathway where we have this destructive interference, because there is negative sign over here, so this will reduce the intensity to zero, nearly zero, so we don't see any response. So that means that we are having a quantum interference between these two different pathways. It's nice. So we know that what's happening. So the next question we ask is, why do we see this twofold axial response in this system, because so far no one has seen this kind of response. So what's the underlying physics associated with this system? So we try to understand these open questions. So we ask this question: what drives the axial Higgs mod in this material, and what's the nature of this unconventional CDW order associated? So if you look in the literature, we can have a different type of vector orders depending on inversion and time reversal symmetry. Which symmetry we break, which symmetry we preserve. So if we break time reversal symmetry, we have a magnetic order. If we go from paramagnet to ferromagnet, that breaks time reversal symmetry and can be this kind of vector order. But if we have a ferroelectric system and we break inversion symmetry, they produce this polar order. So in the case where we break both inversion and time reversal symmetry, we can have a ferrotoroidal vector order. But another case is a ferroaxial order, where we preserve both inversion and time reversal symmetry, but break the mirror symmetry and rotational symmetries. So to know what's the nature of this unconventional order in this system, one needs to very carefully look over the symmetries. Which symmetries are broken, for example, translation, rotation, mirror, spatial inversion, and time reversal symmetries across the CDW transition. So how we did that? We first tried to understand the theory. So we built a we extended the Gunzburg-Landau theory and built a microscopic model that what kind of model can explain or what theory can explain the detection of this axial mod. And then we did experimental probe, we use experimental probe like Raman, TEM, and second harmonic generation, and also mu-SR measurements for time reversal symmetry. So first I will discuss what theory tells us. So with the help of theory groups, we built theory, the microscopic model, by considering a non-trivial orbital order. So if we consider this tellurium scale mat where this charge density wave order appears, so these two lobes are the px and py orbitals, and the gray color show that the charge density is uniformly distributed all over the area of px and py in the normal state where there is no CDW order. So what happens? We can write down the equation for the charge density in terms of the amplitude of the px and py orbital and the phases. So now we have a charge density for px orbital and py orbitals. We have separated these two. So what happened for the conventional scenario? So conventional scenario, we have equal amplitude and equal phases. Amplitude means the charge on the px charge distribution on the px and py orbital. They are in phase and also have same amplitude. So this in this case, as I shown over here, this type. You can see distribution. So now px and py orbital, they have the same charge. So that's why the color over here is red. And then the CDW appears and we have a charge modulation. So charge modulates along this direction, vertical direction, and it modulates equally in px and py orbitals. So this will break these two mirror planes, because this is a unidirectional system. It's obvious that if you have a unidirectional CDW, that breaks these two mirrors. But we have preserved the other two that vertical mirrors. So this is the conventional scenario. So now if we extend the theory, the case where we have unequal this amplitude of the charge,